Hey guys, welcome back to the channel. Today we'll dive into quicksort and explore how this powerful sorting algorithm works and breaking down its efficiency step by step. Let's start with a quick summary of how quicksort works before jumping into the animation. Quicksort is a comparison-based sorting algorithm that uses divide and conquer approach. First, it picks a pivot element from the array. This pivot is the key to partitioning the array into two subarrays, one with smaller elements than the pivot, the other with the larger elements than the pivot. The partitioning process ensures that pivot is moved to its correct position, with smaller elements on the left and larger elements on the right. Next, quicksort recursively sorts the left and right subarrays around the pivot, applying the same process on each smaller partition. On average, quicksort has a time complexity of n log n, making it very efficient for larger datasets. However, in the worst case, like when the pivot is poorly chosen, it can degrade to OF n square. Despite this, quicksort is still efficient for larger datasets because it sorts in place, meaning it doesn't require any extra memory, which helps its memory usage to be very low. Now, let's dive into the animation to visually explore how quicksort works in action. Alright, let's get started. The first step in quicksort is to choose the pivot element, which will help us partition the list. While we can technically choose any element as the pivot, to keep things simple, we'll always choose the last element in the list, as this makes the process easier to follow. In this case, we choose element 4. Now we set the initial pointers for I and j, that is I equals to -1 and j equals to 0, that is the first element, number 6. Let's compare. 6 is greater than 4, yep, so we don't swap and move j to the next element, that is 5. Next, we check 5 is greater than 4, again, yes, so we skip the swap and move j to the next index, that is element number 3. Now comes the interesting case, 3 and 4. 3 is less than 4, so we move index I to the next position, that is element number 6, and then swap 6 and 3. This makes sure that the elements smaller than the pivot are on the left. Moving on, we move j to index 3, where we find 1. Is 1 greater than 4? Nope. So we move I to the next index, that is element number 5, and then we swap 5 and 1. You can see that the smaller elements than the pivot are moving to the left. Next, j moves to next index, that is element 8. Is 8 greater than 4? Yes, so no swap needed. Just move j to the next index. Now we check 7 against 4. Yep, it's greater. So again, no swap required. We just move j to the next index. Again, the interesting case, 2 and 4. Is 2 greater than 4? Nope. So we move I to the next index, that is element number 6, and swap 6 and 2. Whenever j is less than the pivot, we move I and swap I and j. Now, j loop ends, we move I to index 3, on that is element number 5, and swap it with the pivot, which is 4. This ensures that pivot reached its final position. And boom, the pivot is in place. The list is split into two partitions and we are ready to move on to the left partition. We apply the same process to other partitions as well. Let's dive into how partitioning works. The main idea behind quicksort is to divide the list into smaller chunks so we can sort them independently. And that's where the partitioning steps in. At each step, we pick a pivot here. It's the last element and our goal is to move all the smaller elements to the left of the pivot and the larger elements to the right. So we start with 2 pointers, I, which tracks the boundary of the smaller elements, and j, which goes through each element one by one. Whenever j finds an element smaller than the pivot, we increment I and swap the elements I and j. This ensures that the smaller elements are moved to the left side of the pivot. If the element is greater than the pivot, we simply move forward, keeping the larger elements to the right. At the end of this process, I points to the last smaller element than the pivot. We then swap the pivot with the element at I plus 1, ensuring the pivot is placed to the correct position. Everything to the left of it is smaller and everything to the right of it is larger. The beauty of this step is that we have now split the array into two smaller partitions, one with elements smaller than the pivot and another with elements larger. We'll recursively apply the same process to these partitions until the list is fully sorted. So in short, partitioning is about finding the right spot for the pivot, then separating the list into smaller sublists that can be sorted independently. That's the core of how quicksort works. Now, as you can see on the screen, the array is almost sorted and we have successfully placed all the elements in their correct positions. The quicksort algorithm continues to break down the problem into smaller partitions until the array is ordered. And that's the magic of quicksort, efficiently sorting larger data sets by dividing and conquering. Up next, let's take a quick look at the code behind this process and break down each step in more detail. Let's take a closer look at the code that powers our quicksort algorithm. First, we have a partition function. This function's job is to pick a pivot and partition the array into two parts, one with elements smaller than the pivot and one with elements greater than it. The first line selects the last element of the array as pivot. Then we initialize I equals to low minus 1, which is the boundary for smaller elements than the pivot. We use a for loop that iterates through the array from low to high minus 1, comparing each element with the pivot. Inside the loop, if an element is less than or equal to the pivot, we increment I and swap the current element with the element at position I. This ensures that smaller elements move to the left of the pivot. After the loop finishes, we place the pivot in its correct position by swapping element at I plus 1 with the pivot. This puts the pivot in the middle with the smaller elements on the left and larger elements on the right. This function returns I plus 1, which is the index of the pivot in its sorted position. Now we move on to the quicksort function. The quicksort function is a recursive function. It checks if low is less than high to ensure that there are at least two elements to sort. If the condition is true, it calls the partition function to get the pivot index. After partitioning, quicksort is called recursively on the two halves of the array. First for the left side of the pivot and then for the right side of the pivot. Finally, in the main part of the program, we define an initial array and call the quicksort function and print the sorted array. And that's the basic structure of how quicksort works in code. Each function plays a key role in dividing and sorting the array, and this recursive approach ensures efficiency. Up next, let's take a quick look at time complexity of this algorithm. Here we have a graph showing the average time complexity of quicksort, that is n log n. As you can see, the graph slopes up as the input size increases, but not as steeply as the other algorithms like bubble sort or insertion sort, which have a time complexity of O(n)². This means quicksort is much faster for larger datasets. For comparison, merge sort also has a time complexity of n log n, which is similar to quicksort. However, quicksort tends to be faster in practice due to its in-place sorting, meaning it doesn't require any additional memory like merge sort does. In worst case, quicksort's time complexity can degrade to O(n)² if the pivot is poorly chosen, like when the list is already sorted. But with the good pivot selection, like using a median or something, quicksort usually performs very efficiently. In general, quicksort is preferred for many real-world scenarios because of its speed and low memory overhead, making it ideal for sorting large data sets. And that concludes our look at quicksort. Thanks a lot for watching, guys. Hope you found this helpful. If you enjoyed this video, make sure to hit that like button and don't forget to subscribe. I'll see you in the next one. Until then, keep learning, keep coding. Thanks again.